Okay, great.
Okay, then we have the next talk by Santiago. Please take it away.
Thank you very much. Okay, hello everyone. Today I'll be talking about a work called on preservation of speculative constant time by compilation. My name is Santiago Arranz Olmos. The other authors of the paper are Gilles, Barthe, Lionel, Blatter, Benjamin, Gregoire, and Vincent, Laporte. In this work, we study speculation, as in hardware speculation, branch prediction, and in the context of security. And we show that a proof of concept compiler that we mechanized in CoC preserves non-interference properties even under speculation. The three main takeaways of this talk are that we model speculation and side channel leakage in a verification-friendly way. We use directives to model predictions inside the CPU. So when you face a branch, you might take the correct path, the usual sequential path, which we model as a step directive, or the processor might mistakenly predict the wrong branch, or an adversary mistrain the predictor to force you to take the wrong branch, and we model this with a force directive, and then execution is indexed by a sequence of directives that guide control flow. The second main takeaway is that we study the interaction of speculation and compiler transformations, usual transformations that appear in compilers, and we use directive and observation transformers to establish the usual compiler simulation diagrams and prove preservation of side channel security. Finally, we provide a core compiler mechanized in CoC with 9 compiler passes and show that it preserves non-interference. As a quick motivation, I will go over the most basic Spectre example, which is the problem with speculation and side channels. Here we have a program that has 2 arrays on the stack, A and B, that has secret and public data respectively. And the program performs a comparison between an index I and the size of an array. It then loads from the array at this index and branches on that. As we saw earlier, this can be a branching on Y can be a problem because we are leaking the value of Y. We are leaking whether I is equal to 0 or not. However, since B contains public data, this code is what cryptographers call constant time, meaning that the execution time of this program is constant regardless of the value of secrets. The execution time is independent from secrets. The sad part is that because of speculation, because the processor might infer that the branch is going to go in, you might execute this branch even when I is out of bounds. And you might access memory outside the bounds of B, even to A, for instance. And you might read secret data and branch on that. When the CPU realizes that this prediction was wrong, it will roll back and it will do the correct computation. However, naturally, microarchitectural state is not rolled back, so the cache is still there, and we can still perform side channel attacks on misspeculated executions. This is what's called a Spectre attack. The usual way of reasoning about side channel security is to have semantics like this, where we have a state S that steps to a state S prime and produces an observation O above the arrow. The O is what an adversary can measure about the execution of your program, be it time, consumption of power, or whatever. For our purposes, we will have 3 kinds of observations. So addresses, when you perform a load, for instance, here from A at index E, what gets leaked is the array, be it the base pointer, for instance, and the evaluation of the offset, P. So the address that you access, this is for cache attacks. The other kind of observations that we have are for conditionals, loops, branches in general, where branch conditions, here the evaluation of E gets leaked. This is observable, because this is observable by an adversary from outside, but via timing attack. Instructions that do not leak via timing, such as assignment, for instance, leak nothing, and we represent this with an empty observation, which is nothing. In this framework, constant time then means that O, which is above the arrow, should be independent from your secret data. To take Spectre into consideration, we need to add something to this picture. So we have a semantics similar to the one before, where we have S and S prime B states and O and observation, but now it's indexed by a directive D, which represents the prediction from the branch predictor of the CPU, which is adversarially controlled. Many instructions do not need any predictions, such for instance loads. So then they take the step directive, which is just the usual step of execution. Conditionals, loops, and branches in general take a force B directive. This represents the prediction of the branch predictor, and you see that here we are leaking as before the condition of the conditional or the loop, but the branch that gets executed depends solely on the prediction, not on the state, which is the prediction is given by the adversary. And lastly, the third kind of directive that we consider are for out-of-bounds accesses, which are very common in misspeculated execution. As we saw in the example, you cannot check for a variable being in bounds. The adversary can issue a MPI directive forcing the program to access array B at position I instead of what the programmer intended. This is because when you are accessing out of bounds, you might access at different points in time, different regions of memory, depending on how the compiler laid out your stack. With this framework, now speculative constant time, which is constant time even under speculation, means that for any behavior of the predictor, that is for all D below the arrow, we have that the observations that the attacker can do, O above the arrow, must be independent from secrets. Previous work has established that for a compiler to preserve constant time, we can use the usual compiler simulation diagrams, where we want that if the source program is constant time, the compiled program should be constant time as well. And we say that, and the usual compiler simulation diagram says that we have a target state T that steps to a target state T prime and produces an observation OT. And we show that for any source state that is related with the target, it can replay a similar action and still a similar step and still be in relation with T prime. Now, the key to constant time preservation is to relate these observations, OS and OT. If we introduce a function f that explains target observations in terms of source observations. By making this link, we ensure that if OS contains no secrets, a function of it, which is OT, can contain no secrets either. To take speculation into consideration and to preserve Spectre countermeasures, now we have directives in the target. The target performs a step with respect to a particular prediction. And now our job is to establish a similar simulation, but we also need to find an appropriate directive to make the source perform the step we need. For this, we introduce another function, G, another transformer, that takes the target directive and tells us what the source should do to give us the step we need. G guides the source speculation, taking into consideration what the target has done. This is the essence of our approach and the way that we proved our compiler, by establishing these two functions for each compiler pass, these two transformers. The general statement of the proofs is that we have a source and a target programs S and T. We have a pair of indistinguishable inputs, that is, they coincide in their public data, I1 and I2. And we have an execution of the target on the input T1 under these directives D, meaning this prediction behavior. And we want to find an execution of the source that allows us to explain the observations that the attacker saw at the target. For this, we need to find G and F, as I mentioned before. The generic part is that G and F can depend on I2, an indistinguishable input that coincides in the public part with I1. This allows the transformer to look not only into what the current step has been for the target, but also on public data, which is important from some passes. Interestingly, this approach of establishing disparate transformers for each compiler pass is complete in the sense that these two functions always exist if your compiler transformation preserves speculative constant time. We illustrate our approach with a proof of concept compiler with 9 simplified but representative compiler passes, such as constant folding, dead branch elimination, array reuse, and RTL generation, where we had to use all flavors of the simulation diagrams, lockstep, many to one, many to many, and introduce a few more other technicalities. In this talk, I will talk just about 2 of them. First, constant propagation, which tracks the value of variables and replaces their uses by the values. Here we have x that receives 3, so then the compiler will look at the uses of x and replace them by 3, for instance, there in the load. If we are careful with how we do our analysis, this pass can preserve speculative constant time. The basic intuition being that the leakage from an access to A at index x plus 4 and the leakage from an access to A at position 3 plus 4 is the same, A7. I said that we need to be careful with our analysis because when we track the value of x, we cannot assume that branches will go the way we expect them to. We need to over-approximate those soundly. To establish the simulation diagram that we need for this pass, we choose the transformers G and F to be the identity. The programs are in lockstep. Every step that the target performs, the source can replay exactly. Expressions evaluate to the same values, and thus observations contain no secrets. The second pass that I will talk about today is dead assignment elimination. In this program, we have x that receives 3, then the result receives x plus 4, and then it gets overwritten by 2. And dead assignment elimination removes unnecessary assignments that do not contribute to the result of a program. So here we can just remove the first 2 and keep that the result is 2. The idea behind this pass preserving speculative constant time is that dead variables don't influence leakage, otherwise they wouldn't be dead. But this has the caveat that we still need to be careful when performing our liveness analysis. We need to take into consideration that branches don't go the way we expect them to. The simulation diagram for this pass is a bit more interesting because the source needs many steps to catch up with the target. This is because the source needs to execute the dead assignments before it can replay the useful instruction that the target did. The transformers, the directive transformer, for instance, takes the target action and needs to insert step directives before that to execute each of the dead assignments before it. In our case, it will be 2 dead assignments, so that's 2 steps. And the observation transformer needs to remove the bullet observations from the dead assignments and just keep the significant one at the end. I will be brief so that we can go for lunch. So I will summarize now by revisiting the main takeaways. Directives help us model non-determinism in a nice way, such that we can construct functions like the transformers, and we can tackle non-determinism introduced by the predictors in a trace-by-trace manner. Transformers simplify the proofs of hyperproperties because they, being functions, they allow us to consider 2 executions, a source and a target, instead of 4, 2 indistinguishable sources and 2 indistinguishable targets, as would be needed for a hyperproperty like constant time. And we show that many compiler passes can preserve speculative constant time if we are careful with our analysis. We exemplify this with a mechanized compiler in Coq that you can check out in our work. There is a link. And with that, I can move to questions. Thank you very much.
Thank you very much for the talk. Any questions?
I have a question about, so first, thank you for the talk. I have a question about the dead code elimination you had in there.
Yes.
So you said that variables don't influence the leakage, but I mean, are you eliminating possible memory reads or something like that? Or is that like out of scope?
Yes, that's a good question. No, so we do not consider those instructions as that. You can, if you want, consider that ones that leak public addresses, you can consider them as that, but then your analysis needs to take into consideration security annotations or how you want to annotate your program, which we decided to just take the standard way of analyzing programs without knowledge of what's public, what's secret.
Okay, so then I'd just like to generalize the question. So in general, if you have some leaky code, are you tampering with it in your compilation, or is the leaky code always, does it stay the same?
If I have code that the basic idea is that if I have code that leaks, I can remove it. My result leaks less, so it's fine. I can transform it such that the leakage of my transform program is a function of the source leakage.
Okay.
The idea being that, okay, if I was okay with leaking that in the source, I'm also okay with leaking a function of it. If I'm okay with leaking my address, I'm okay with leaking just my house number.
Okay, thank you.
I have one question. So you say that your FNG always exists.
Yes.
Which is really cool. That you also have a general construction of constructing FNG, like with I give you a pass, like you can somehow automatically construct that, or do you still need to come up with that?
No. You need to come up with them for them to be nice to work with. Okay, so they exist, but the way that you show that they exist is that basically the interesting part is the way back. I know that my pass preserves speculative constant time. How do I get the functions? And the basic idea is that, well, I know that my program is constant time. Given that I know the public data and I know the directives, I can replay the program myself and I construct my functions in that way.
I see. So you would have like the full program or something in the functions.
Basically, it's a function per program. The function is the program that tells you what the leakage is.
I see. Okay. Yep. Makes sense. Any other questions? Okay. There are no more questions. Then let's thank the speaker again.
Thank you very much.